Okay, let's start. So let's review what we have done last time. So last time we talked about how to graph the function and how to change the perspective of the function. So let's summarize what we have done and what we are going to do. So to graph the function z equals to fxy with custom perspective. So first of all, we have to find out the way to rotate our perspective. So our method was to rotate by y-axis first and then rotate by z-axis. With these two angles, I can change any perspective. So first of all, rotate the canvas. So this canvas was originally perpendicular to x-axis, and I was rotate by y-axis and then by z-axis. So that was our scheme. And after we rotate our canvas, so recall that our canvas is like a transparent canvas, and I'm going to look at my 3D object through this canvas as if it's projected onto the canvas. So I have to project my 3D object, whatever that is. For each point on the 3D object should be projected onto the canvas. Project the 3D graph onto the 2D canvas. So the reason why I'm putting the canvas as a capital letter is that this canvas is lying in this 3D space, but we are going to draw this canvas in 2D plane, right? That's how we that's how we draw the 3D object in the paper or in this blackboard or 2D thing. And then that's it. And then so the third step is that whatever that is projected onto this 2D canvas, I have to make it in this file, which gives you 2D picture. So draw the projection, or should I say, just draw the object in canvas to the file, image file. Okay? So that's our three-step method of drawing things. So we have kind of done the first step. So let's rethink about how we did it. So we have x, y, and z. So my canvas is going to be perpendicular to x-axis. Last time I was thinking as if it's located distance from this 3D object, which lies in somewhere here. So let's say our 3D object is somewhere here. Well, this is not a graph or function. I'm just giving you a random figure here. And you can think that my canvas is somewhere at here, but since you are going to project 3D points in 3D object onto this plane, you don't really need to put this in away from this origin. If you're going to project everything on this plane, you can just simply put your plane at the origin, the plane passing through the origin. So I'm going to start my canvas as same as YZ plane. So this is when x equals to 0. This is my starting point of my canvas, right? And I rotate it by y-axis and z-axis. That's we implemented in the last time. And then think about the normal vector to this plane. It was x-axis, which was 1, 0, 0 vector. So after we rotate this normal vector, we'll also rotate accordingly by y-axis and z-axis. And then let's draw rotated canvas here. So after rotation, we will have somehow this kind of picture. So when you rotate plane passing through the origin by y-axis and z-axis, the result plane also passing through this origin, right? So this red one also passes through the origin. And here is our same figure. Okay. And well, you see the 3D object can pass through this plane, the canvas, but that's okay because this is just imaginary canvas. I can project it onto this plane. And now we have different normal vector to this rotated plane. Let's say this is V, okay? Or I will give a different name in the code, but let's, well, usually the normal vector is represented by n, so n for normal. And what we are going to do is pick a point or any line, because it doesn't matter if you pick a point, then line is the line is the thing that connects two points. So it's enough to pick any point that you want to draw. And think about way to project point, 3D space, to this plane. So I'm going to project this point onto the plane. So I'm going to draw another picture, a better picture. So suppose that my plane, so rotate this axis and then put this rotated canvas in this configuration. And then this is our normal vector. And then let's say we have a vector here. And let's say this is the origin. Okay. Here is a random point, x, y, z. I want to find out the position inside of this plane when I project my point in 3D space onto this plane perpendicularly. That means parallel to this normal vector. So let's say we have x prime, y prime, z prime. Let's call this name v, and let's say this is v prime. So we have information about the direction of the plane with the normal vector here, and we have a random vector. I want to find out the position of the point when I project this point onto the plane. So what's your idea? How are you going to find these points?
v vector is the minus n vector. So use this so we can estimate to v vector.
So we know the coordinates of v vector, and we want to find the coordinates of v prime vector. And what's your name? Sorry, Jaehyun? Yes. What Jaehyun said is think about position vector from the origin, these two vectors. So I will call the same name for these red vectors. This is v and this is v prime. When I take v minus v prime, this will parallel to the vector n. So we are going to somehow use that fact. So good idea. And let's see. I know that this line, which is, this one is actually the v prime. This is v prime minus v vector, right? I know this is parallel, but I don't know the length of this vector. So the thing is, I have to find out the length of this vector to find out the v prime coordinates, right? So let's see. Let's take this one as what we don't know yet. But we know that this is parallel to n, so we know that this is c times n, right? So I know that v prime equals to v plus c times n because of this assumption here. And what's the relation between v prime and n? They are perpendicular. They are in a right angle position. So what kind of equation can you set up with two vectors which in the perpendicular position? Inner product is 0, right? So n inner product with v prime is equals to 0. So let's combine these two equations. We have n inner product. Let's replace this v prime with v plus c times n, and that is equal to 0. And n times v is equals to minus c times n inner product with n. So inner product is distributed in this summation. So now we know what c is. So c is minus of n inner product n inner product v. So this n is already given. We know this vector by rotating the 1, 0, 0. And v is given as the point in the 3D object. This is what we choose in the beginning. So we can definitely calculate this constant c, and if you plug in this constant inside this equation, we know what v prime is. We're going to use this equation. Okay. All right. So we know how to project a point on the 3D, 2D canvas, and then think about how to draw that into the canvas, because after all, what we are going to see is this red plane, rotated plane, as if you're looking at this plane in the same direction of this normal vector, right? So when you draw any picture inside 2D plane, you have to assign xy coordinates in this 2D figure. So what's the xy plane, xy coordinate system in this rotated figure? So originally it was y-axis and z-axis. This is x and this is y inside of this canvas. This xy axis is also rotated accordingly with y-axis and z-axis, right? This y-z axis is the axis for 3D object, and this xy axis is the axis for 2D canvas. Okay, so I should give a different name in this code, but let's for now give the same xy because that's what we usually call it for understanding the plane. So this is the normal vector, and there are y-axis inside of this canvas, which is rotated also, and here is x-axis. So think about where this y-x vector comes from, as if it's a 3D vector. Although I'm considering these vector as a 2D, the axis in this 2D figure, we have to consider this xy axis as if it's a 3D vector because this plane is lying in 3D space. So where does xy axis come from? It comes from y and z axis in 3D space, right? So this y is rotated from what? Y-axis, which is 0, 1, 0. Okay. So I'm taking the unit vector parallel to y-axis. And how about x-axis in this canvas? Oh, sorry. Y-axis comes from z-axis, right? 0, 0, 1. And x-axis comes from y-axis. So this is from 0, 1, 0, right? So we can find out the x unit vector to the x-axis direction and y-axis direction as a 3D vector by taking the rotation of 0, 0, 1 and 0, 1, 0. Okay? And then I have to find out the coordinates of point projected onto the canvas according to this xy axis inside of canvas. So let me draw another picture. So I have v prime. Okay? Here's my plane. Now it's upright. So let's say n is coming out of this blackboard. Okay? And let's say v prime is somewhere pointing here. So v prime is lying inside of this plane. And here is our x and y, which is rotated 3D vector from 0, 0, 0, 1, 0, 0, 0, 1, right? So let's see. Let me give a name for this. So x-axis is when I keep moving along this direction, and y-axis is along this direction. Let's say this is S1 and S2, okay? So S1, S2 are vector, rotate from these two vectors. How am I going to find out the coordinates of v prime inside of this figure? So I'm taking this S1 and S2 as if it's 1, 0 vector and 0, 1 vector inside of this 2D plane. Okay? But actual vector S1, S2, these vectors are 3D vectors. And this figure is lying in 3D space. And v prime is also 3D vector. That's good, very good idea. Did you understand what Jaehyun said?
I understand, but I'm thinking about my opinion. I'm not ready to answer.
Answer, okay. But you agree with this idea that what he said, what Jaehyun said is, since v prime is linear combination of S1 and S2, right? So we have to find out what C1 and C2 are. These will going to be x coordinates and y coordinates of the point corresponding to V prime inside of this 2D canvas. So we have to find out how to find the C1 and C2. So let me ask another student. How are you going to find C1 and C2 in that case?
I didn't actually understand.
Which part? Which part you didn't understand?
Just finding C1 and C2.
Mm-hmm. You didn't understand why finding C1, C2 gives X and Y coordinates in canvas? Okay, so good question. So, so this is what we're going to plot in PNG file or JPG file, okay? Whenever we're going to plot anything, we have to give a coordinates to the point, right? So we are starting from the center is the origin, and we need to let computer know or this program know that my point is located at X coordinate, comma Y coordinate, right? However, we are in 3D space, okay? This plane lies in 3D space. We're simply looking at this plane inside of 3D space as if it's projected on this plane, okay? So my S1 vector becomes the vector parallel to x-axis, and S2 vector becomes parallel to y-axis inside of this 2D plane. So there are other independent vector to this plane because we are in 3D space, but we're going to ignore that. The vector that we are going to ignore is the normal vector to this plane. This normal vector, which is coming out from this blackboard perpendicularly, is not visible because we are looking right on this direction, right on this n direction, right? So we can just simply ignore the n direction and just looking at S1 and S2. Right? And this will be our picture. So I think compare this figure here. So we had an object in 3D space. We're going to project onto the plane, and we are going to look at this plane in n direction, the normal direction. Right? This is the result when we're looking at this plane in the normal direction, and we have to plot that in 2D image. We have to find out the coordinates. The coordinates is given by the vector in this plane is given by linear combination of two vectors, which are unit vector to x direction and unit vector to y direction. Okay, and these coordinates is the x and y coordinates. Think about simple argument from the high school mathematics. So we have xy plane, right? If you have x comma y, that means you're moving your position from origin to the horizontal way by x unit of unit vector, and then move your position to y direction by y unit of unit vector to y, right? So this is 1, 0, and this is 0, 1. This can simply take the x times of 1, 0, and y times of 0, 1, right? This is the x and y coordinates. We are doing the same thing, just replacing these 2D vector with 3D vectors. Okay, so that's that. And then how we're going to find C1 and C2. Do you have any idea?
Do we know the angle between V prime and S1?
We can by using some property of vectors. How would you find the angle between two vectors?
So we need two equations to find C1 and C2.
Right. So one way is if you know the angle, then you can find out at C1 or C2 somehow. Angle is not given. So this is very good observation, because how would you find the angle between two vectors? Of course, we cannot measure this because we are starting with the random vector v prime. Do you have any answer from Zoom? How do you find the angle between two vectors? V prime and S1, for example. Or in generally, how inner product.
So if we know the norm of the vectors, we could calculate with the relation of inner product.
Right.
So we could find the cosine theta.
Right.
Then we calculate the arc cosine. So we find the set.
Exactly. So an inner product gives cosine of angle, and this gives the idea why we care about the inner product. So basically, this is a philosophical question: why people care about the inner product in vectors. So vector is not just a tuple of numbers; it has a geometric configuration. Inner product, although it's a simple algebraic equation, gives the geometric position or geometric configuration or information about geometric configuration of two vectors. So think about the inner product first, V prime and S1. So we assume that this is the linear combination of S1 and S2. Let's replace that here, C2, S2, inner product, S1. And what happens here? We have C1, S1, inner product, S1, and C2, S2, inner product, S1. We have something disappear in this summation. Yes, the second part disappears. Why? Right, S1 and S2 are orthogonal. So this becomes 0. So we only we're left with this first amend. And what's the inner product of S1 and S1 itself? Say it again, sorry.
The square of the norm.
Square of the norm.
S1.
Yes, exactly. So square of the norm. This is the general definition, and I put the norm as this symbol. And for in this particular case, think about where we had S1 from. We had it from rotation of 0, 1, 0. When you rotate vector, does it change the length of vector? No. So what's the length of S1 vector? 1. So this will be simply S1. So what we did is we take the vector that is projected onto the plane and then simply take the inner product with S1 to get S as C1. Right? And for C2, what should we do? Same as the previous part. So when I take the inner product, this gets C2. So we have C1, C2, which becomes the coordinates of canvas, coordinates inside of this 2D canvas, and we're done. We simply, if we can implement all of this algorithm to the computer program, then we can find out how this 3D object looks like when I change my perspective. Okay. So from now on, so question. Okay, that was the answer from the last question, and that was also a good answer using inner product. So before I move on to the programming part, this gives all the essence of what you learn from linear algebra and vector calculus. So about the inner product, why we need inner product, what does the inner product implies, and so on. So there are much more. There are other properties that you can find in the common textbook, but that follows from these ideas. All right. Any question before we move on to actual computer program? Any question from here? Gotcha. Yes.
This part, we want to get the C1 and C2, but we do this inner product that the result is the C1. So why this using the program this?
You mean why do we need a program to calculate the inner product?
Something that
You can say in Korean.
그러니까 뭐지? 이 V 프라임 벡터에서 C1 벡터하고 C2 벡터를 구해하는데 지금 내적으로 한 값이 그대로 C1과 C2인데 이거를 정확히 말하면 구했다고 보기는 어렵지만 이걸 어떻게 프로그램에서 이용하는지 그냥 네.
That's a good question. So what you're going to do with the C1 and C2 after that. So in the program, what we have done previous lecture was to graph the function in 2D plane, and I showed you how to graph a point or line connecting 2 points. In that, whenever I want to graph something, I need to give the program the x and y coordinates of the points. Once I know the coordinates of the point that I want to draw in 2D plane in xy coordinates, I can let them to plot the point or plot the line connecting 2 points. So these C1, C2 will serve as xy coordinates to tell program to draw the point or line connecting them. So this part is the thinking part, and we have to implement after this more, actually carry out the graphs. So let's see the program here. So we don't have any more question in Zoom, so let's move on to the programming. So I think this is where we left last time. So I will going to make a big picture of what's going on, and then fill out the details. So there are two ways to draw the picture. One is that I'm defining my function and then do everything inside of this function. Or the other way is sometimes I want to draw two graphs in the same figure, a same plane or same canvas. So I can define a canvas object and then let canvas object to draw the function. Okay. So let me do the second way. So because that's simple. Because in the defining of function, I don't need all these parts. I just need a formula of the function and domain of the function and number of variables of the function. And also in the plane, in the canvas, I need a canvas object here. So let's make a canvas. It's a sum module. And I'm going to make type canvas as a struct object. And here we're going to have a plot as a plot pointer. So this plot pointer is we have used for plotting here. So we use the plot package given by gonum.org. And then when we define a canvas, we have to find out how big is my file size is. So the size will be the array of, so I have to go through this thing here. Let me give a little bit search here. Please wait a few minutes. So let me find out. So sometimes when let me show you this. Let me share this video here. Okay. So let's see. Plot. In this plot, when you save this plot, you need to specify the width and height of this file size. So it's given by a length type in VG sub package. So if you go to the length here, type length is same as font length. Well, let's just use the VG length here. So let's go back again. VG length. Okay. So it's an array of VG lengths. So first one will serve as a width, and second one will serve as a height. And how about the others? So we need a file name, which has a string. And that's it. So what I'm going to implement is whenever I have a canvas, I want to graph a function which is given by MBF type. So this canvas object has every information that I need to draw the plot in this plot package. So let's see, nothing wrong here. It just means that probably I didn't install this yet. So I have to go get gonum.org and v1 plot. So let's leave it here. And whenever you make a struct, you have to provide it with a new struct name. So I'm going to give new canvas as a function that spits the initialized canvas pointer. So the thing that I'm putting in front of this name means that I'm going to retrieve the pointer of this struct. So if I have to explain the pointer, I'll probably do the best job because I'm not in CS. I'm not a programming expert. But basically, the pointer means that it gives you the address where the struct is located. It's not the struct itself. So you're not looking at the value, but looking at the address or the location where you're storing this object. So why do I need this pointer? Because I want to observe the same object all the time by looking at the address of the struct. If I'm not putting this asterisk here, then I always have to copy my struct object, and then that might cause some problem. So in the new canvas, always returns the address of canvas. So initialized as, so the plot is given by plot new, and size is, let's just see, I think it's VG length of 400 and 400. And then file name will going to be at default test.png. So you can change this information later in the main function. Okay, so we're going to graph this. Let's see. So it's a graph function. Later. Okay, so not now. All right. Let's see. Okay. Let me give this name. So. All right, so I think I should do this. I should implement graphing here, right? So let's see. First of all, when I try to graph some function, I have to specify the angles of rotations. So I need two angles. One is for rotating about y-axis, the other for z-axis. So my angle will be in array of floats. And let's put a comment here. So when I put a slash, this gives the comment of the function, comment for anything, but if I put it above the function, it gives the comment for the function. And let's see, put here. So T is the array of angles of rotation, y-axis and z-axis. Okay. All right. So, and then let's see what I have to do next. What should I do next? I have to rotate my plane, right? The plane was originally had a normal vector 1, 0, 0, and there are two other vectors. One is the x-axis vector and the other is y-axis vector in the canvas. So that corresponds to 0, 1, 0, 3D vector and 0, 0, 1, 3D vectors. So all of this together with this 1, 0, 0 vector becomes the three normal unit vector of three-dimensional space. So I'm going to define it as a E0, E1, E2. So I'm going to make E as a array of, did I define the vector yet? No, I haven't defined the vector. So I'm just giving you undefined struct for now to be defined later. But for now, just define it as a vector. So I didn't define the vector struct yet, so it simply says there's nothing defined here. But anyway, so and then I'm going to define E as a float, array of floats as 1, 0, 0, E1 as float 64 as 0, 1, 0, and E2 as float 64 as 0, 0, 1. Okay. And then what I'm going to do is rotate these three vectors. So rotate rotation of E0, which is 1, 0, 0, will give you the normal vector of rotated canvas. So I do this for E0, E1, E2. So 1 to 0 to 3, we have I plus plus here. And after rotation, I will define a different symbol. So let's make S as our new name. Vector. So it's an array of 3 vectors. And SI is spherical rotation of vector EI with these 2 angles, so T. Okay, so T was the array of 2 angles. I'm going to use it as the same argument in the spherical rotation function. So this function is about the vector rotation, so I'm going to define it inside the vector package. So I haven't defined yet, even I didn't announce this function yet, so there will be an error message here. But let's keep moving because I just want to give the whole algorithm set up as a setup before I fill out the detail. So once I've done this, what's going to be the S0? So S0 is the normal vector of rotated canvas. So canvas. Okay. And what about S1? Is a unit vector to the x-axis of the canvas. And how about S2? This is the y-axis, unit vector to the y-axis. Okay. Now, we need to find out the point, right? First of all, let's draw this axis first. So how about the x-axis is not moved at all. So when I want to draw the axis, I have to plot the line connecting the origin and this 1, 0, 0, and 0, 1, 0, and 0, 0, 1, right? So I'm going to plot the axis on the canvas. So when I plot things, I have to start from EI. So EI didn't change from our first definition. It's 1, 0, 0, 0, 1, 0, 0, 1, 1, 0. And I'm going to project onto the plane, which is normal to the n direction. So n direction is the S0 vector here. So this is going to be the vector projected onto the plane. I set it as V here. And then in order to draw things about this V vector, I have to find out the coordinates C1 and C2, right? And I'm going to take a V inner product, let's say inner product with S1, and this is going to be my C1, and this C2 is a V inner product with S2, okay? So we have C1 and C2. I don't need the origin because origin is the origin when I project it onto the canvas. So from now on, it's simple the plotting here. So when we have a plot, when we want to plot anything, define it as an XYS. So XYS has X0, Y0, and X. Now it's a C1 and Y is C2. And then, so this canvas already had the field, which is the plot. So I'm going to add the plot here. So first, define a line. So it's C plot, new line with the points. And then, I'm sorry, not plot, sorry. So just the plotter, new line. And then C plot add line. So it's plotters not imported. It's imported. Okay, so everything disappears. So there's some error message above. That's what we have not defined. So we're going to fill out this part. And then we did for 3 axes, right? So we're going to see the 3 axes in the rotated canvas. So this is our bottom figure. And then we're going to draw actual graph of the function. So now, in order to graph function, the last time we used the mesh grid, right? We have a mesh plot. So from 0, I will going to be the index for the x-axis, x array. Let's see. I think I should define it a little bit further here. Let's say n is the integer field, which is given as the number of subdivisions in each axis. So let's initially set up as 20. So from 0 to c.n. So whenever you want to access to the fields in this struct, you put the dot in between. C.n means the n is of the struct C. So I++, and for j from 0 to j, from j to c.n, j++. And I have to find out the value of z. So my z is given by f of x and y. So I didn't define my x and y. So here we are the fixing x. So x is from the start value of the domain, right? So in the MVF struct, there is a domain field which stores information about the interval of x and y coordinates, right? So first array is the array of x interval, the left and right limit. So we have it starting from here, and then we have a number of subinterval as n. So this will going to be a float I times. I think this can be just I, but just leave it here. And then f dot domain 1 minus f dot domain. The right limit of the x-axis and the left limit of x-axis is the length of subinterval, a total interval. I have to divide it by number of subinterval, which is n in C struct. And this gives the equally distributed array from the leftmost value to the rightmost value of x array. And that's fixed. And we are going to set y as similar. So I'm going to copy here. Instead of starting from the zeroth array, I'm going to use the first array. So first array of domain gives the array of y limits. So same thing here with the y. So here we have 1 and divide by same number of subdivisions. Okay, so I think it's done. And when you access to the formula, you have to find out the formula field formula. And the formula takes the array of values, so we have to make it as an array of floats with x and y elements. And array, the return value is also array, so we have to use the z0 as our function value here. And then let's see, from now on, let's draw things again. So points are the plotter, x, y, s. And we are going, let's see. X, Y, oh, let's see. I have to draw the point, I have to draw the line, not the point. So I have to erase this one, and let's see. Let's put y0 and y1. So the reason why I'm doing this is I need 2 points. So I have to draw 2 points. So one is j's and the other is j plus 1s. Okay, so z0 is from x to y0 and z1 is from x to x comma y1. That's the value. And before I plot anything, I have to change it to the C1, C2 coordinates, right, in this canvas, right? So let's say my V0 is a vector of x, y, z coordinates, which is x, y0, and z0, okay? So again, the reason why I put the index in z0 is because the function f has the formula which spits the output value of the formula is always the array of float values. So I'm using the first one because I know that this function will going to be output has one single variable. And V1 similar but with a different inputs, so it's going to be 1 and z1. Okay. So we have a v0 vector and v1 vector in 3D space. I have to project it onto the plane and then use the coordinates of c1 and c2 here. So use the similar thing here. So what we have done is to using projection plane function and then take the inner product, right? I could have done this more efficient way, but let's do the not hard way, but it's just inefficient way. Projection plane. Where is it called? Projection. Project plane. That was the name of project plane. Okay. So project plane onto our normal vector, and that will give some results. Okay. So I will store this to W0. Give a different name here, and then same thing. For W1, I'm going to project V1 to the plane with normal vector S0, and here I have to use see, it's really nice, not a good way to do this, but just to give a every time giving a different symbol is not a good way to do this, but I will change this later. Inner product with what? Take the inner product with S1, right? It's the same thing here, saying S1. And C02 will give you the W0 inner product S2, okay? The same thing for W1. So instead of C0, we have C1, C1, 2, and now we are ready to plot this. So I have to use C01, C02 as the x and y coordinates of first part. And the second point that I'm going to draw the line is that C11 and C12. Okay. It's a semicolon. Okay. All right. Then, oh, I didn't use W1, so this should be W1. Okay. And then draw a line connecting these points. PTS. And then add that line to our canvas. So we need another, this only gives you the line through the x-axis, right? We need another, the line plotting on the graph of this function. But for now, let's test whether this works well. Before we test, let's remove all the error messages here. So why this error came from. So I didn't define the vector struct in our vector package, so let's make one. So here, I'm going to make a vector.go and package vector, and I'm going to define a vector as an array of floats. Okay. So this vector has some function which should be defined. First one is inner product with another vector, and the result is the real number, so it's a float. So for I from j 0 to v, so I'm taking a general vector, so I don't know whether it's a 3-dimension or 4-dimension. Doesn't matter because I'm just taking all the arrays of vectors, and then take v1 and vi and wi multiplied each other. I'm going to add this summing as multiples. So first of all, let's store that summand in sum. So I'm declaring my sum variable as a float 64, and it's initialized as 0. So sum plus is going to be adding all this and return this value. So this is the easiest way to implement inner product, but sometimes you have to handle the error, because sometimes people try to inner product two-dimensional vector to three-dimensional vector. That will make a problem. So let's see, if the length of V array is not equals to length of W, so len is the predefined function which counts the number of arrays, a number of elements in these arrays, then we have to panic. So this is also usual way to handle the error. Invalid inner product. So whenever this panic happens, it will terminate the program. Okay? And then what we have to do is try to define the project plane. So project plane function. So project plane function takes the normal vector as an input, because this is all we need to know. And then it spits out another vector. Okay. So let's look at our calculation. We need to calculate C, right? So C is the negative of V inner product with n divided by what? N inner product with n. Okay. So I can't do this just I can do the inner product by taking simple dot after n, because n is defined as a vector, and then vector has a method that can be called by putting the dots. Okay. All right, and then what? I have to return the v prime over there. So I have to set the new vector. Let's see. It's going to be easy if I define new vector. So it's going to be just a creation function. So with the n elements in the array, so v will be array of floats with n elements and return v. That's all. So w will be just a new vector with the same number of elements in v, and then each element will be simply given by the arithmetics of v and cn. So wi will be vi minus plus c times what? N, right? And you have to return w. All right. I think that kind of solved the situation. So, so I have to import the vector sub package. I'm sorry, not vector, matrix. Vector is just a struct name. Sorry, vector is correct. Vector is the name of module, right? Vector here. So let's wait a little while. So this is vector, not vector. Vector. I didn't define three quotation yet, so let's do this. All right, so let's go to the vector here and function vvec spherical rotation. So I need two floats, and then result is also another vector. So we did this in the previous time. So we had a main function, and we defined two t's, and then we define matrix. So we're going to use this matrix as what? This is rotation about y-axis, right? So let's okay, so before we do this, let's make another here. So so first of all, I have to make a matrix multiplication. So let's see. Let's define W as a new matrix, new vector with same number of elements in V. And then we have to define a rotation about Y first. So we're going to define matrix multiplication to the vector W. So we're going to call rotation matrix about T0 angle on y-axis. So y is just an argument that I'm taking to tell this computer that I'm going to take about y-axis. I have to define the function called the rotational matrix. I haven't done this yet. And then take a multiplication with the W vector, but usually you cannot take the multiplication between matrix and vector. You have to make the vector as a matrix. Let's recall what we have, how we have done. So here we define the vector as a matrix, right? So that's why we could have just simply multiplied these matrix and vector. But here we define the vector as simple array, one-dimensional array of floats. So we have to somehow make it as the matrix. So let's define two matrix function here. So two matrix is the conversion of the matrix to vector to matrix. So this gives the matrix object, and we're going to use a column vector as a matrix form. So we're going to take M as a matrix, new matrix of how many rows we need is same number of elements in V, and we need one column. Okay, for I from 0 to I less than, and len of V I plus plus, and mi0 will be the same value of vi. So 0 is the zeros column. So we have single column. We have only single column. So we're only changing the value for the row. So we have return m, and that's it. We have done the multiplication and rotational matrix. We have to define on the matrix goal because that's about the matrix. So function rotation matrix. It takes argument about what string or what axis are going to rotate about, and also the angle. So angle t is the float, right? So and then it spits out the matrix. So it depends on the axis string, which matrix you have to return. So first of all, let's define a matrix in 3 by 3 form, and then you have to split the cases when axis is defined as string of x and string of y or string of z. So in that case, usually we use this syntax, so switch, and then case when we put y, of course we need x, but we're not going to use that. But let's implement here. I'm not going to write anything when x is called. I don't know why it's lagging, but it's having a small lag. In that case, I'm going to use this definition in the main that we have done previous. So we have matrix here. So it's going to M. And in the case of C, we're going to use this, right? All right. So and then this will be all T, not T1. Oh, where did I put? Okay, so in the case of Z, okay, and then return M. So M2 is going to be just M. All right. This simply gives the rotational matrix, okay? So I make it into separate function so that it's simple. So, all right, so let's remove all the error messages here. Where's error message? Here. Okay, so spherical rotation, I have not finished yet. So I start with initialized vector, and then let's see. I'm taking vector V and rotate that. So I have to copy that to W. So I'm not using vector V to rotate because that will alter the previous vector. So I'm going to make a new one and then copy that to copy the previous one to the new one. So Wi will be Wi, Vi, and then first make a multiplication, and then after you rotate, apply the multiplication, store that to W again. I'm sorry, so it's not W, sorry. So it's just let's say M here. So the result is a matrix M. And then apply the rotation matrix, all about z-axis with angle T1, the second argument of the angle, to the result, M. Okay. All right, so that's going to be in a matrix form, 3x1 matrix form. But we want the result to be the vector form, so I have to make it to vector. Okay, and that will be our result. Return. So I haven't defined two vector function. This makes the matrix to vector, so I have to define it again here. So function M matrix to vector is a vector, and V is new vector with the same number of rows here. So for I from 0 to I length of V, we have Vi equals to Mi 0. All right. So return V. Okay. So everything works well. So spherical rotation, let's check again. So we have two angles input, and we have we copied the vector V to W, and then make a matrix multiplication with rotational matrix about y-axis, and then rotational matrix about z-axis, and return it as a vector. Okay. So we'll go back to the canvas here. Spherical rotation now should work. What is it? Spherical rotation. So spherical rotation doesn't require some normal direction, right? So we had spherical rotation takes only the array of angles here, right? Arrays of angles. T is given by float array. Maybe the typo, spherical rotation, right? Ah, okay, sorry. So this is defined as the method of vector, so this is the results. So I'm going to take S1 SI vector and then take the spherical rotation about T angles. And then, wait. So I'm not taking ES, I'm taking EI and take a spherical rotation and then store to SI. Okay, that's the way it should go. All right. So and then let's go below here. Here's a typo. Project plane, and then okay. Everything should work fine. So graph has no output, so that should be it. And let's see. Let's define another function. So C canvas has a save function. So it simply saves into the file. So C plot is the field in C which has information probably about graphing the function, and then I'm going to save it to so C has size, which is in VG length array, so takes the first argument as the width argument and second one as a height argument, and then the last one is the file name argument, which is stored in the file name field, and that's it. So we have graph function and save function. So let's go back to main. All right. So first of all, I have to define my function, MVF type, in order to call any graph. So erase this, and then I'm going to define a new MVF. And whatever it goes, I have to leave it here because I didn't define this function yet. But let's define C again. So new, so it's in the canvas package. So it's a new canvas. And then C.graph F, and then I'm going to save. So this is all we have to do. Define function, define canvas, graph it, and then save the file. So new vector, new MVF, have to define here. Sorry. Okay. New MVF. All right. So what do I need? I need a function takes the array of floats and then splits the array of floats. And also I need a number as an integer array. So it's an array of number of independent variable and number of dependent variable. Okay, so I have explained why we need this array. And domain is array of two arrays, a float. All right, and then it gives the pointer of MVF type. Okay, so it returns the MVF pointer of formula is F and number is NV and domain is DOM. Okay, that's all. Actually, we don't need this. Well, you can define a graph function as a method of this MVF, but we already defined the graph as a method of canvas object. And this is it. So let's go to main again. And in the MVF, we have to define a function as simple function. Let's say X array and spits out float 64. And how it defined is the following. So it returns the array of floats. So it's just single elements array. So x0, 0, x0 times x0, and take a minus x1 times x1. Sorry, it should be bracket. So new MVF is in MVF package. So this should be how it go. MVF is called. So error message will disappear soon. And then, okay, so this is first argument that we have to put. And the second argument was number of variables. So we have to put a number of variable is 2 to 1. And third argument was the domain, right? So domain of floats. So floats, let's see, start from -2 to 2 for x-axis and then -2 to 2 for y-axis again. All right, so here we have -2 to 2. And that's the end of the argument. Let's delete here. Here's an error message, small error message. Let's see. Expected statement found. Okay, so I forgot one parenthesis here. Parenthesis ends here. Okay. And then let's see. C graph has more argument. Oh, it needs the angle of rotation, right? So let's put the angle of rotation as a float values. So first angle rotation, let's say we want to take the same angle that we observed last time. So what was it? The mass dot arc cosine of mass square root of 2 minus divide by square root of 3. And then the second one was mass dot pi over 4, right? So these are two value of floats, 1, 2, messed up pi over 4 and 2, okay. And then we need the second argument as MVF type function, okay. So the mass is imported, so it should disappear soon. All right, so there's one more message, one error message. So let's see what it's saying. Cannot use FFMVF and value in the argument to graph. So let's see. In the canvas, the graph function takes array of floats and array of function MVF type function f. Let's see. In the main goal, we define function f as MVF type with a new MVF function. And let's see what happens to new MVF function. New MVF, okay, so it returns the pointer of MVF, okay? So I have to make it, I have to make an argument as a pointer too, so you have to take a pointer argument. All right, so then we don't have any error message. All right, let's run. Go run main.go. Probably, usually it doesn't work. Okay, so no error message. Usually you don't get an error message here. Okay, so it's quite a nice picture. We didn't delete this axis here. So there is an XY axis up here. It's in the figure. But it's good. So you asked why we need C1 and C2. That's why we need C1 and C2, because everything we plot in this 2D plane or PNG or JPG file is according to the XY plane as if it's in the left and bottom here. Okay, let's make X and Y coordinate disappear. Okay, so we have plot here, so it's about plotting. Let's see, maybe we can do this way. Plot.new, and we're going to have a little, so we have plot new. Why is it? Okay, so hide axis, okay. And then I'm going to assign P as my plot. Okay, so, and then we have a comma. We should have comma here. And then let's run again. Look at the test P. What? It's not done yet. Okay. So wait a while. So now we have no more thing here. So you see there's a small axis inside of this, in the middle here. That's the XYZ axis. If you want, you can put a label on it. But you see this XY axis looks symmetric here because we did a 45-degree angle rotation. What if we had a different angle rotation? So we can change it by assign different value. So let's see. Maybe I can put pi over 3, or maybe pi over 6. That should be more dramatic. Where's my mouse? Okay. So and then save it and run again. Let's look at let's wait until it updates. So this was previous figure, and this is when we rotated about pi over 4. And now new figure is when we rotate about pi over 6. You see the axis, XY axis are a little bit tilted, right? And you see the lines which lies on this graph of plane, a graph of function, right? If you want the better picture, you should put a line in the different direction, in the y direction, I mean the x direction. These lines are drawn in the y direction only. Okay. So you see, but I think this is a good picture in this case because I used the x squared minus y squared function. But you see this looks like horse saddle, like the thing that you put on the horse, on the back of the horse when you ride a horse. So this is called a saddle. Okay. So we have a few minutes. So let's make it our code a little bit neater. So because we had a canvas graph and actually if you want to graph another function, then you shouldn't put your axis when you draw the function. It has to be done prior to graph the function. So let's put it this way. So let's say we want to draw canvas, draw axis here. Or let's see, in other in the other perspective, in the other thoughts, it will make a problem if you graph a function in this perspective and the other function in the other perspective. But this function takes the angle of perspective when you draw the function. So I have to pick this t outside of this argument because this will make a problem. So let's say I want to make it here. So it's inside of canvas, I have to make an angles as a field. So and then in the initialized angles here, float 64 as mass r cosine, mass square root of 2 divided by mass square root of 3. And then what we have, I forgot the parenthesis, and we have mass pi over 4. This is, I will take that as a default configuration, so that's why I'm putting here. So by doing this, I don't need the angle anymore because it will stored in my canvas object. So whenever I need, I will just simply call t as c dot angles. Okay. So no error from now on, but let's see, I want to take the axis drawing out of this graph thing. So P here, but still I need these SIs in order to take a projection and also find out the C1 and C2. So I'm going to copy this and paste here. So let's see. Do I need T? I need T. Okay, so but I only used T here, so I can simply replace C angles here and then delete this line. Okay. And then everything works fine. Okay, so no error. And let's see. S1, S2. Okay, so far it's okay. So I'm trying to make concise as possible. So when the graph function part, it's too messy. It's hard to look what's going on here. So I'm going to make it as simple like this. So first of all, what I'm doing here for x and y and z is I'm making an array of x values in the x direction and y direction in these intervals. So I will make a new function called, so x is going to be array of this line, these points in x-axis. So there is a linspace in the MATLAB. If you have learned the MATLAB last semester, there's a linspace function. I will just simply replicate this. So it will make equally spaced array of x values from the leftmost limit and the rightmost limit with n number of subdivisions, Cn, okay? And then store it as an array. So I haven't defined this linspace. Let's define it here. Linspace. So you don't have to define you don't have to define the struct whenever you define a Go type. So Go function. But if I define my linspace function inside of canvas.go, it will make difficult to read what's going on. So I will make a separate file. So linspace takes T0 and T1 as float values. And the last one is number of subdivisions, okay? So I will make, so the result is array of floats, okay? So array of floats, 64. And then, let's see, the return is C, return name is C. I will make float 64 with n+1 arrays for I from 0 to, I don't know why I have lagging, because I'm not running anything. But let's see, I from 0 to n. The reason why I put the equal sign here is because I have n number of subdivisions. That means I have n+1 array of elements. So Ci will be same as our previous formula, so which is float 64 I times T1 minus T0 divided by float 64 of n, and then return C. Okay, so that's our linspace function. So using this linspace function, I can do the y here, and y is from 1. Y array is in interval of y array is in the first array of domain. Okay. So and then let's erase this, and okay, I can also erase y0 and y1. So now the first value of z is when I plug in xi and yj. All right. The second value is x is fixed, but y value is the next value of the array. So this is z1 and z0 and z1. And all right. So I should make it as a vector. So let's put it here, I, j, and here is I and j plus 1, okay? So two vectors. And let's see, what else I can make it simpler. So this V0 is a vector which has a project plane method. So I'm going to take this project plane at the end of here, dot project plane. So instead of assigning this vector into new argument, new symbol, I'm just taking this vector right, and then this apply this project plane method. And this project plane method will give another, let's see, vector, and then same thing for this part. So we have project plane as 0. Okay. I forgot comma here. So I don't need this assignment. But now I have to find out C1s and C2s. So let's try to make it this way. So for now, whatever I'm going to do after this is going to define a point. So let's define point as a plotter, xy's as 2. And for I from 0 to 2, I used I, so I have to use another symbol. So here is k. I have to use it k as my increasing argument. And the case point will be plotter xy of the following values. So x will be C1 value and y will be the C2 value. I have to compute the C1 and C2. So let's say I will have a function that computes for me. So whenever I have the vector, I will store it to v. Did I use v in? Okay, so I haven't used v, so I can use it. And then I'm going to take v coordinates. So let's say coordinates of v respect to S1 and S2. All right. So I'm going to take C0 and so coordinate is a function that splits the coordinates of C1, C2, which defined by inner product. Okay. So I haven't defined it yet, so that's why we have a red line here. I will define it later. And then I assigned my points to be a plotter xy type with these elements, x and y's are in this way. So I have done this for k0 to 1, not 2, just up to 1. But when I do this, I only want to change the index of j. Okay. So then it's done. So I don't need anything here, down here, right? So I have points defined, I have a line, and I add a line. So let's define coordinates. Let's define it in this file. Coordinates is taking a vector v, so it's in the vector, dot vector, and 3 vectors, right, actually. So it's v and E0 and E1, okay? So just name it E0, E1, okay? And then it splits the array of floats. So it returns the float values. The first one is v inner product E0, and second one v inner product with E1, and that's it. Okay, so we have imported vector, and this disappears, and everything works fine. So we have one more error. So we have Z1. You haven't used this. I don't need this, right? Actually, I need this inside of here. right? So when I compute my z value, I have to change my index of y. So let's put plus k here. So z0 is my value of the function. Okay. Okay, let's go to main. So now we don't need two arguments of angles. We simply need to graph the function, because the angle rotations are defined already when I make a new canvas. So run main.go. All right, it's done. Test.png. Okay, so I forgot to put the axis here because I split my drawing axis part in different functions, so I have to draw axis. Okay, and then let's do it again. Where's it function? Where's file? Okay, so it's still processing. So it's done. We have axis appears right here. Everything looks nice. Let's rotate more. I think it's gonna be an end of it. So when you want to rotate, and you have to say assign a different angle. Angles is float 64 of, let's see, mass pi over 4 and mass pi over 4. Okay. Go run main.go. So this was previous picture, and when you rotate in different angle, you see that there's a small change in the perspective and also in the configuration of graph. All right, this is how you implement the graphing calculator, which takes a different angle of perspective. So before we finish, let me summarize what we have done here. So why we are trying to make this graphing calculator? First of all, we started with a motivation that we want to see the limit, what's going on with the function, weird function at the 0, 0. What's the limit of the function when x, y goes to 0, 0? And in order to find out, we need a more precise version of graphing calculator. The previous version cannot change the perspective. We wanted to change the perspectives to understand the graph of function better. And meanwhile, when we designed this graphing calculator, we talked about every aspect of vectors, inner product and projections and so on. And then once we have a graphing calculator, what can we do with it? Not just the limit, but we can also look at the tangent planes, and also we can look at the rate of change in certain direction, or also you can draw two different graphs in the same plot, or you can plot a parametric curve lying on this graph of function, and so on. But later, after the midterm, we are going to talk about the integration, and when you integrate over a surface, we have to use this graphing calculator. So this is not the perfect one, but you can also modify a little bit so that you can use better in your own object or your own goal. Maybe you can choose this as your project subject, or you can just do it for fun. So anyway, this is it for the graphing part. And the next time we are going to talk about continuity and the what is it called? In the single variable function case, we had a differentiability of the function. In the two variable or multivariable function, you also have the differentiability of the function. So we're going to talk about that next time. So maybe we are not going to do more this kind of programming this much from now on. Do the exercise or do some other project part on your own. All right, thank you for listening and see you on Friday.